Today we're going to start our fourth topic of the class. We're going to talk about branching processes. And we're really only going to talk about one particular type. It goes by the name of Galton-Watson process, named after two people. I think, in my opinion, this is probably a topic that kind of needs a new name. It's named after two people, Galton and Watson, and I don't know so much about, well, really either of them. I'm not a historian, but I know a little bit about Galton, and like high on his list of things he's known for is eugenics. And this topic kind of sprang, I think, from that interest of his, but it has lots of other applications, which is why we look at it. So you should just be aware of that. It's probably something that mathematicians and statisticians should maybe consider naming after somebody else. But in any case, so we're going to focus entirely on this one particular type of process. And I introduced it last time, and I'm going to introduce it again and give some notation, some sort of more careful notation for what this is about. So the idea is we want to think about some sort of population of objects like particles or people or other things. And so let's represent an example object from that population with a little circle on our drawing here. And let's say that on the left side, so time is going to progress as you move to the right on the drawing, and so we're going to say that for us, at this time, at the initial time, we're going to suppose that the population was 1. So we'll say that x0 is equal to 1. You don't have to do that. You can start with more than 1. And so we're going to on the bottom here, we're going to have a horizontal axis that represents time. And so we'll use n for that because it comes in discrete jumps. So this is like generation or time. And the idea is that each one of these objects in the population has a chance of producing more objects, so reproducing basically. And so here this is going to be, we're going to start at n equals 0. So the sort of first generation or the 0th generation for us is going to have a population of 1. And so after a bit of time, we'll split off, well, we may, each element of the population has a chance to split off or to reproduce. And I'm going to use a little rectangle for that. Maybe I'll use like a highlighted symbol. Make it a little smaller. But so this particle goes forth, or this generation goes forth and has a chance to reproduce. And so let's represent that reproduction moment or something by this little blob of color here. And so we'll suppose that this one did, and it turned into, it produced 3 more objects. And so I'll draw those out like this. Oops. So this little pink thing is meant to be the branching event. Let's see if I can move that. Like that. It's a little better. And then after that, each one of those guys, each one of those lines points to another element of the population, or an offspring, as they call it. And so we'll separate this is time equals 0 on the left. I'll use gray here. And then this next batch of 3 is the second, or I don't know what you want to call it, the first group of offspring, or the second generation. So we'll call this, we'll say that n is equal to 1 here. And the population, which is counted by x, which is the variable we're primarily going to be interested in, this guy's equal to 3. And each one of these guys, each one of these offspring has their own possibility of branching or creating more offspring. And let's just suppose, for sake of argument, that only one of them does. So let's say that this bottom one does, and the top two don't. And so this bottom one just produces 1. Oops. So we'll draw this off like that. And I'll just duplicate this guy. And so now we're at the third generation, or the second time step if you want. And we're back to having only one member of the population here. And then there's another chance for these guys to spring off. And let's say that 2 come off at this point. So each of these little pink blobs is like a branching event. And we've got 2 that are here. And the idea is that we want to kind of study what happens to this population over time. And so we're going to do that with a few different tools. But so here at this moment, x sub 2, this is just sort of defining our notation. We've only got 1. And then here at x sub 3, we've got 2. Like that. And so this thing continues. That's the whole idea here. This process continues. Now, I want to introduce another symbol that doesn't really appear much in your, well, I think it doesn't really appear at all in your notes, but it appears in the proofs. And it's used to calculate what happens, what is the x at these various different moments. And these are going to be capital Z. And so we'll say capital Z represents the number of offspring produced by, and then there's 2 labels that go along with that. Which offspring was it in a current generation, and when was that current generation? So you could kind of put 2 indices on this Z quantity. You can find different notation in different places. You don't really need to keep track of everything, but I kind of like to. And so I'm going to say that over here, I'll label this in red. We'll say, so here, Z, so from the first, well, how do I want to say this? The first element of the population at this time, there's only one element, so we'll give his Z1 is going to describe for us how many offspring came off from this guy. And we're going to put a time label on here of 0, because we're starting at time 0. We're at time 0. And so this guy's equal to 3. And similarly, we can introduce 3 different Z quantities for this generation, 1 for each of the current offsprings. And so we'll do that. So we'll say Z1 at time 1 is equal to Z2 at time 1, and that's 0, because there were neither of those members of the population branched or produced an offspring. Or you could say that their branching output was 0 or something like that. And then this last one, the bottom one, we'll say that guy, so that's Z3, and then again we're at time 1, that guy was equal to 1. So the third element of the population at that time produced an offspring. And then for this next section, we could keep on going with this. So I think this is only one we can finish now. So we've got, for this guy, there's only one element of the population at this generation. And so we'll say Z1 at time 2, oops. And the number that it produced was 2. And I can't put any more z's down because I haven't said what happens in the next generation, how many of those got produced offspring, and so on. But so this is the notation that I'm going to use. I think it's okay. And the thing we're going to be calling the process is x, the counting of the population at the different generations. So the process is going to be the set of x sub n's, and n is non-negative integer or natural number. Some people call this natural number, like that. And you might think that, well, I don't know, it seems plausible that we would start this discussion by looking at the transition probabilities. So you might try to compute, or you might imagine that you're kind of interested in. So this is like, do we want this? You might be, do we want the following things? Are we going to try to compute things like the probability that xn is equal to some number I sub n, given that xn minus 1 is equal to some other number? And it turns out we won't really do this. We're going to use probability generating functions instead. So not really. Use PGFs. So that's going to be our kind of primary tool for talking about these branching processes, is probability generating functions. I want to emphasize that it's not necessary that x0 is equal to 1. So I should put that up here. This is not required, so not always. Not always 1. But that's what we're using here. So you can imagine you start with some population that's bigger than 1. Okay, and so you can write a formula for how do you define x at a different time. And so we have the following. So x at some time bigger than 0 is going to be a sum over an index that we'll call k. And so k goes from 1 up to, and so what we're trying to count here is we're trying to count all the z's. So let's say I want to know what was the population here, right? x1, so x at time 1. What I'd be counting up are all of the z's from the previous generation, or maybe it's better to use this other example over here. So if I want to know x at time 2, the way to do it is to add up this guy, and this guy, right? And so the way we're going to express that is we say this is a sum over k, and k starts from 1, but it goes up to a number x n minus 1. So the size of the population at the previous step, each one of those has a z associated with it. And then we just count up the z's. So then we put under here z sub k, and the z's are from the previous generation, right? And you'll see this written, I think in the proofs, the z's are kind of written with only the subscript. So sometimes you see it written like this. Without bothering to label that you're saying that you're talking about the z's from the previous generation. But I don't know, I find it's better to be explicit, and it's not that messy. I think it's a little bit, but not too bad. Okay, and then we're going to require that each of the z's, so z sub k, n, each of them is independent and identically distributed. And they take on, of course, non-negative integer values, and they can't be negative numbers, because that's a perfectly reasonable thing to sort of imagine. but so we'll suppose they take on non-negative values. Integer values. So there's no half particles that come out or something like that. Okay, and so we'll write that the probability, or we'll write the probability mass function for these guys in the following way. So in other words, each one has this probability mass function, probability that z is equal to, I guess I need another letter here, so why don't I just say m. That's going to be lowercase p sub m. So this is the same for all of the different z's, right? And this quantity here, this probability mass function, is called the offspring distribution. Right, so each particle or each member of the population as you go along here has the same, is governed by the same rules for how many particles or offspring they might produce at their branching event. Okay, so we'll proceed in our usual way, which is to introduce a proposition and then prove it, and then string along a series of those. So the first proposition that we're going to introduce is a proposition that describes the probability generating functions for the two different types of random variables that we've introduced. And so this is a proposition. And so let's define the probability generating functions first, and then we'll state the relationship between them. So let's let the following. So we'll use the symbol f with a subscript of n to be the probability generating function for x sub n. All right, so again, this is for a Galton-Watson process. Xn, and then n is 0 or higher. And we're going to start with x0 equals 1, which is not always required, but we're going to do that, right? So that's what these variables xn are, just like introduced before. And we'll suppose that this funny looking f sub n is its probability generating function. And so in other words, just as a short reminder, f sub n of s looks like this. So it's a sum of over k starting from 0 up to infinity, or wherever it stops, s to the k times the probability that x sub n is equal to k. Okay, and then I just want to remind you, we can write this as an expected value of s to the x sub n. Right, that might be handy sometimes. All right, so that's just introducing one probability generating function, and we'll introduce the next one. The next one is going to get the symbol g. So f has an index for time because it varies with each time, but the z's, and this one's going to be a probability generating function for the z quantities, these are governed by the same probability mass function, so they're going to have the same probability generating function, g of s, be the probability generating function for any of the z's for the offspring distribution. Right, so in other words, G of S is equal to the sum, it's just the definition, K equals 0 to infinity, S to the K, and the probability that Z is equal to K. And that probability mass function is the same for all of them, and so this is the same. Now, we typically won't know this quantity here, or at least we haven't seen it, the probability mass function for the population size, but we typically will know the offspring distribution. Okay, and of course you could write this as well, expected value of S to the Z, like that. You could write that. Okay, and so here's the proposition. All right, so that's just introducing the PGFs that we want to actually talk about. And the proposition has three parts. Okay, so this is the proposition. Then the following is our claim. So first of all, F1 of S is the same as G of S. Okay, that's the first part. The second part is that F at some later time is equal to this kind of nested expression. So there's going to be a G, and then inside that there's going to be another G, and inside that there's going to be another, and so on, up until you get to the last one, and its argument is going to be S. And then, of course, there's a bunch of parentheses over here to close all those off, right? And the idea here is that there's n different G's in this thing. Okay, so that's part 2 of the proposition. So each of these is some relationship between the PGF for Z and the PGF for X sub n. Okay, and then part 3 says that F sub n evaluated at S is equal to G, where its argument is the previous F evaluated at S. All right, those are the 3 parts of our proposition. All right, so now we'll go ahead and work through the proof. So the proof, and we're going to just go through it in order of the part of the proposition. So the first part of the proposition says that the PGF for X1 is the same as the PGF for Z, and that's relatively trivial. So for 1, if we just write out what is X1, right, so this is the sum over the index K starting at 1 and going up to X0, and then Z sub K at generation 0. But we've required that X0 is only 1, and so this is actually just equal to Z sub K, Z sub 1 for generation 0. And so, in other words, X sub 1 actually is one of the random variables that we had called Z. And so, therefore, by uniqueness, they have the same probability generating function. So F1 of S has to be the same as the probability generating function for Z1, which is just G. Right, so this is the PGF for X1, and this is the PGF for G, because they're actually, sorry, not for not for G, for Z, for any of the Z's. And so these guys are the same. All right, the second part is a little more interesting. So we're going to use this rule that we had introduced in the first week or so of the class on compound probability generating functions. So I want to remind you what that was. So recall, because if you think about it, these branching processes are actually, they're clearly related to this. In that case, we were talking about like a fish. The fish had a bunch of eggs, and then there were some they were independent, identically distributed events telling you how many, telling you, what was it? Telling you whether or not the egg, well, let's write it down. So this is an eggs example. So this is for compound probability generating functions. Or this is what we called this, I think. And we called the sum, we called it the total. We said this was a sum over k. And it went up to n, which was a random variable. The number of eggs that hatched was a random variable. Just like in our case, x is a random variable. And then we've got x sub k here, like this. Right, and so the rule was that, so n was a non-negative integer, non-negative integer valued independent of the xk's. So that was one of the requirements. The xk's were identically independently distributed non-negative integer values. And we have that here as well. And the result of this, so this, for this particular construction here, for this construction here, the result was that the probability generating function for t, for the total, with an argument s, was given by this compound thing. So it was the probability generating function for n on the outside, and the argument was the probability generating function for x. Right? So this was something we had used before, and we want to use it again for our situation. But so let's take a look at what we've got here. So for us, the total here, this is going to be like x sub n. This guy is going to be x sub n minus 1. Right, so let's sketch this over here. And the thing that we're calling, so there's some confusing repeated notation here. These guys are the z's. I guess you could call it zk, but they have the PGF that goes along with the offspring distribution. All right, so we're going to apply this rule repeatedly, starting from n equals 2. Okay, so apply starting at n equals 2. Okay. Okay, so what we've got is on the left-hand side, we've got the PGF for, so let's look at this. The total is x sub n, so this is going to be the PGF for x sub 2, and that's f sub 2. And we'll give it an argument s. I'm actually going to label the argument here sub 2 as well. You don't have to do that really, but I find it helpful because we're going to start merging things. And so that's equal to this compound thing. So how is it made up over here? So here we've got the PGF for this random variable, but this random variable in our case is going to be the previous x, right? So that's going to be, that PGF is going to be f sub 1, right? And its argument is going to be the probability generating function in this case for the offspring. So it's the offspring PGF. So we've got G and then S2 like that. All right. But then by the first part of the proposition, this is actually just equal to, so remember f sub 1 by part 1 of the proposition is just G. By part 1 of the proposition, the thing that we already proved. Okay, now we're going to repeat this, and we're going to look at the n equals, so this is like n equals 2. Now we'll look at n equals 3, and so on. And so I've got f sub 3. I'll label this s sub 3. I think maybe you don't really need this, but I'm going to give myself a little bit more room. Right, and so this guy, we followed through the same procedure, and this is just f sub 2 evaluated at G of S3, right? But this quantity f sub 2, we already figured it out, right? So what we want to do is basically, we want to take this quantity here and put it into the argument for s sub 2, right? And see what we get. And then, and using this expression over here, right? And so what we get is G evaluated at G, and then I'm putting in s sub 2, replacing it with G of s sub 3. Like that. Okay. And then we just repeat this process, right? So over and over and over again. And what you get in the end is f sub n of s is equal to, and then the thing that we were after. So you just build this up from the bottom. I think you can also do it by induction if you wanted. Maybe that's harder. And again, you've got n different times. N different copies of those G's. So now we're ready to go on to the last part of the proof. So part 3. Oops. Right, and so we're going to start by using something from using the previous thing. So from the last part that we just proved, so from part 2 of the proposition, I'm just going to take this result that we just created. We've got, and I'm going to evaluate it at n minus 1. Right, this guy is equal to, and so let's just repeat, let's just steal this. Just like that, except it's not n times, it's n minus 1 times. Right? Okay. And then similarly, I can just keep doing this, but I'm going to evaluate this at n, so I'll just take the exact copy of this. Right, so if I've got that, I can do that. But now look, so let's move this label. How do I want to do this? I'll just do the following. Right, so if there's n copies of G there on the right, then if I just look at the interior ones, count those up. Right, so I'm neglecting to count this one there should be n minus 1 of those. This is borderline proof by picture. Right? And therefore, this is equal to G f n minus 1 of S. Right? Just by stealing the line above. All right, and that's the end of the proof. You can give yourself a square if you want. So now let's go on to our next proposition. We're going to say something about means and variances next. So I'll give myself some space here. And we're going to spend the rest of the lecture working on this one proposition. So we're going to say, suppose that you've got a Galton-Watson process. Just like we've been doing. And we're going to have it start with 1. So all right. Suppose that that's the case, and then let's define symbols for the mean and or the expected value and variance for generation. I don't know what you want to call it, 2 or the n equals 1 generation. So now let's define mu to be the expected value of x1 and sigma squared to be the variance of x1. All right, if that's true, then you can write the other expected values and means in terms of these. And so here's the different parts of this proposition. So the expected value of x sub n, it turns out, is mu to the n. And the variance of x sub n is equal to a slightly messier formula. So I'll give us some more space here. If mu is equal to 1, we get special circumstances. So in other words, if the expected number of the expected size for population at n equals 1 is 1, then we get n times sigma squared. So this is the mu equals 1 case. And if mu is not 1, we get a messier formula. You get sigma squared times mu to the n minus 1 times quantity mu to the n minus 1, all divided by mu minus 1. Okay, we're going to work on these two parts separately, so we'll do the proof. First, we'll prove part 1. And this one we're going to do by induction. And so we're going to say, take the base case. N equals 1, right? And this case is trivial because we've been given that the expected value of x1 is equal to mu. That's the definition of mu, right? So we're working on trying to prove this thing here. It's clearly true for n equals 1 because the expected value of x1 is defined to be mu, okay? Now, we'll suppose that it's true for n, that the thing holds for n minus 1. So suppose the following. Suppose that the expected value of x sub n minus 1 is equal to mu to the n minus 1. Right? Now, Now we're going to try to show that it then follows that the expected value of xn is mu to the n. And then we'll be done. So if we go from the previous proposition, all right, so from before, from the previous proposition, we can write out the PGF for n at time n. We can write f sub n of s as this nested thing, g, where the argument is f sub n minus 1, evaluated at s, right? And we're going to use the fact that, so to find the expected value of x sub n, so here's what's in my mind here, all right? We want to use this is the first derivative of its probability generating function evaluated at 1, right? So this is that old tune that we've used a bunch, right? So let's look at the derivative of this. So fn prime of, whoa, man, what a mess. That's just a shambles all over the place. All right. fn prime. So the first derivative of this with respect to s, right? So we just use the chain rule, right? And so we get g prime, and then put in its argument, and then multiply by the derivative of the inside. And so that's f prime n minus 1 of s, right? Okay, so now, so here's what we have. The expected value of x sub n, oops, come on, pen, is equal to f prime n evaluated at 1, and so we'll do that. So that is g prime, and then f n minus 1 evaluated at 1 times f prime n minus 1 evaluated at 1, right? Now, I don't know if you remember this other, so I should say we're using two things for any PGF evaluated at 1, it's 1. Right, so we're going to use that thing for this guy, and then we're going to use this thing for this guy. Okay, and so what we've got is g prime of 1, and then f prime of n minus 1. This was, so let's just write it out. Right? So that's what goes there. But this was, by assumption, mu to the n minus 1. Right? And the expected value, or sorry, g prime evaluated at 1 is equal to mu, because x1, so g prime of 1 is the expected value. Let's just write this out. So this is the expected value of z. But the expected value of z is the same as the expected value of x1, because z and x1 are the same. Right, and so therefore this is mu times mu to the n minus 1, and we've got our result. All right, so the strategy for part 2 is similar. So let's write out the plan first. It turns out to be a little bit long, But the strategy is straightforward. So the strategy is going to be like this, right? So here's our plan, right? We want to use an old rule. I don't remember which lecture it was, but from way back in the preliminaries, that says the following. It says the variance of a random variable, and in this case, the random variable we're interested in is x sub n. You can express that in terms of its PGF evaluated and its derivatives evaluated at 1. And so this thing is something happened to my, sorry about that. So the variance of x sub n is going to be the second derivative of its PGF, so that's f sub n, evaluated at 1, plus the first derivative, evaluated at 1, and that's something we already know how to compute, minus the square of the first derivative, evaluated at 1. Right, so those second two terms we already know how to compute, and so this is going to be, we just did it, right? So the first derivative evaluated at 1 is the expected value, and so this is mu to the n minus mu to the 2n, and then plus this new thing that we've not yet computed, second derivative of f sub n evaluated at 1. And so what we want to do is find a general general form of this last term and then put it in. So we want to find f double prime of n evaluated at 1 and put it in. So that's where all of our work is going to go into for this last part of the proof. All right, so so that's the plan. So we're going to start from the result we already had. So the above result, which is, where is it? Just the first derivative, right? So I'm going to take that and bring that down here. All right, so I've got the first derivative here. And then I want to take the second derivative of it. And so we'll do that, and it gets pretty ugly, but it's going to be fine. Move it over a little bit. Okay, so I take the next derivative of that, and here's what I get. Okay, the second derivative of this guy times the derivative of its inside, but that's already on the outside, so I've got this thing squared. Like that. And then plus the first term times the derivative of the second. Okay. All right. And now we can clean this up a little bit when we evaluate it at 1. Because we're only going to be evaluating at 1. Right, so let's look at all the things that are going to simplify. So when you evaluate this thing at 1, it's a PGF, so that's going to give you 1. When you evaluate this thing at 1, that's going to be the expected value, and so that's going to be a mu sub n minus 1. This is going to be 1, and then this guy we don't have yet. Right, so g double prime of 1, multiplying the expected value, so we can just put that in, so that's mu sub n minus 1 squared, so that's 2n minus 2, or 2 times n minus 1, maybe I'll do it that way, plus g prime, g prime of 1, we already know what that is, right? That's mu. Times f double prime n minus 1 of s, of 1, sorry. All right. Now, we're going to start building these up, building up from scratch the general rule here. So we're going to start at n equals 2 and then move forward. Okay, so now we build. From n equals 2 and look for a pattern. All right, so for n equals 2, put that over here, n equals 2 case. So f2 double prime of 1 is equal to g double prime of 1 times mu squared. Right? And then plus mu times, okay, so if n is equal to 2, that's f sub 1 double prime, and that's g double prime. This is the whole reason for starting from n equals 2. Right? So in other words, this is equal to g double prime of 1 times the quantity mu squared plus mu. Right? And that's the result for that one. Now we'll look at f double prime at n equals 3, and then we'll take this result and substitute into it. So all right, so f double prime of n equals 3, better look back here. And so I'm going to be like sort of reading off this as I fill in the result. So I got mu, so let's see, 3 minus 1 is 2, so mu to the 4th times g double prime of 1 plus mu, and then here's the previous, so this term here is now the previous result. So I've got f double prime of 2 evaluated at 1, right? And so we're going to substitute this guy into there. Okay, and you can probably just see the result, I think. So we're going to get g double prime of 1 multiplying the following quantity, mu to the 4th plus mu to the 3rd plus mu squared. All right, and now we're just going to repeat this over and over again, right? Let's do one more. Why not? Why not? It's always enjoyable to do something where you kind of don't expect troubles. Maybe it is. Maybe it isn't. Right, so for n equals 4, we go back up here and say, okay, well, that's g double prime of 1 times mu to the 5th plus mu times the previous result right, and we're going to substitute that in again. So just drawing, just to sort of remind you what's happening here. All right, and when you put that in there, you get the following simple thing. Simple? I think so. G double prime of 1 times the following quantity. Mu to the 6th. Is that right? Let's see, do I got that right? Did I skip one? me think here. I think I messed up. Where did I make my mistake here? I think it's here. For n equals 4, yeah, that's mu to the 6th. N minus 1 is 3. 2 times 3 is famously 6. Gotcha. Okay. Okay, so then when you put these together, you get mu to the 6th plus mu to the 5th, and so on. Right? And so you can keep on going. All right. So the result f double prime of n evaluated at 1 looks like this. So I'm just going to carry it over, carry on. So I didn't even put my labels here. N equals 3, n equals 4, and just general n. Okay, so for general n, I'll just save myself the trouble and just write down the result here. G double prime of 1 times mu to the n minus 1 sum k equals 0 to n minus 1 mu to the k. So this is, once again, a series that you should be able to evaluate. And so I'm just going to evaluate the series. And you can write the result as follows. You get 2 different results. And then we're just going to stop for today, and we'll finish the proof in the next lecture. There's 2 different results. So it's g double prime of 1 times mu to the n minus 1, and then multiplying these 2 different results. So if mu is not equals to, if mu is not 1, the sum has a simple form, or well, the sum is straightforward. Mu to the n minus 1 over mu minus 1. So that's when mu is not equal to 1. But if mu is 1, that thing is a little bit problematic, and this is just n. Okay, and then we'll finish this next time. But remember, the idea is, so we found this general expression for the second derivative of f sub n evaluated at 1, and then the plan that we're going to put into place is to go back over here and put it here. And so we're going to do some algebraic tidying, and you can see there's going to be 2 different types of results for the 2 different types of f double prime that you get there. All right, that's all for today.